All right, buckle up everyone, because we are diving deep into the world of machine learning today, and we're looking at a paper that's causing quite a stir. It's called the FFT Strikes Back, an efficient alternative to self-attention. Before we begin, please subscribe to get more videos like this. Thank you.
You know what's interesting about this paper is it tackles a major bottleneck in AI, and that is how to efficiently process really long sequences of data. Things like analyzing huge chunks of text or processing high-resolution images.
Yeah? And we all know that self-attention has really been a game changer in AI, allowing models to understand those complex relationships. But the problem is that self-attention, as those data sets get larger and larger, can get really computationally expensive.
Exactly. Self-attention works by comparing every part of a sequence to every other part. And this is great for understanding context, but it can quickly become a computational nightmare. Just imagine a party where everyone has to shake hands with everyone else. It works for small gatherings, but it becomes impossible with a stadium full of people. Right, so this paper is posing a new hero, and that is FFTNet, and it uses this clever trick called the Fast Fourier Transform. The big claim here is that FFT can achieve similar results to self-attention, but much, much faster.
That's the key takeaway here. FFT is all about efficiency, and what's even more impressive, that is, it doesn't sacrifice accuracy for speed. It's kind of like finding a shortcut through a dense jungle. You get to your destination faster, losing your way.
Okay, I'm intrigued.
Yeah.
But before we get too deep into the specifics of FFTNet, let's take a step back and make sure that we're all on the same page about why self-attention is so computationally expensive.
Sure. Self-attention has this thing called quadratic complexity. That sounds very technical. But what it basically means is as the length of a data sequence increases, the processing time grows exponentially. Imagine you double the length of the sequence. The processing time could quadruple, making it really inefficient for longer sequences.
So it's like the longer the sentence, the harder it is for the AI to understand it using self-attention.
Precisely. And that's where the FFT comes in. It offers a way to process the data in a more structured, efficient way, leading to a much more manageable complexity.
Okay, let's unpack this FFT thing. I have a vague memory of it from my college math days, but remind me, how does it actually work, and how does it help with efficiency?
Imagine an orchestra playing a really complex piece of music. The FT is like having a magical tool that can instantly separate out the individual instruments, the violins, the cellos, the flutes, and so on, allowing you to analyze each part individually.
So instead of listening to the whole orchestra at once, you're breaking it down into its individual components.
I can see how that might be easier to analyze, right? And that's essentially what the FFT does with data. It breaks down the signal into its frequency components. This allows us to process those components individually rather than dealing with the entire sequence at once.
Okay, that makes sense. But how does breaking things down into frequency actually speed up the process?
The magic lies in the mathematical properties of the FFT algorithm. Instead of having to compare every data point to every other data point like in self-attention, the FFT allows us to process the data in a way that scales much more efficiently with the sequence length.
So it's like we found a way to organize the data so the relationships become clearer and easier to analyze without having to do all those tedious pairwise comparisons.
Exactly. And this shift in complexity is what makes FTE so promising. Instead of that exponential growth we saw with self-attention, the FFT gives us a much more manageable increase in processing time as the data sequence gets longer.
Okay, I'm starting to see the appeal of this FFT thing. It's like we found a way to streamline the whole data processing pipeline, but it can't be just as simple as applying the FFT, right? There must be more to it than that.
You're absolutely right. The genius of FFT lies not just in using the FT, but in how it incorporates the FFT into a larger, more sophisticated architecture.
Intriguing. So how does FFTNet take this basic FFT idea and turn it into something that can actually rival self-attention in terms of performance?
The key is that FTE doesn't just blindly apply the FFT. It has this really clever adaptive spectral filter that acts like an intelligent conductor guiding the orchestra of frequencies based on the specific task at hand.
Okay, I'm loving these musical analogies. So explain this adaptive filter to me. How does it conduct the frequencies?
Imagine you have a piece of music and it has lots of different instruments playing. The adaptive filter is like having a conductor who can listen to the entire piece and then decide which instrument should be emphasized at different points in time.
So it's like the filter is dynamically adjusting the volume levels for each instrument to highlight the most important parts of the music.
Exactly. And in the case of FFTNet, the instruments are the different frequency components of the data. The adaptive filter learns to emphasize or suppress certain frequencies based on the overall context of the input sequence.
That's fascinating. So it's not just about breaking down the data into frequencies. It's about selectively amplifying or attenuating those frequencies based on what's actually important for the task at hand.
Precisely. And this adaptive filtering is what allows FFTNet to be both efficient and accurate. It's not just about speed. It's about understanding the data at a deeper level, just like self-attention does, but with a more efficient approach. Already blowing my mind. We've got speed, we've got accuracy, and it sounds like we've got a level of sophistication that goes beyond just a simple FFTD application.
And there's even more to it. FFTNet incorporates this special activation function called the mod RealU, which operates directly on complex numbers in the frequency domain, adding another layer of complexity and expressive power to the model.
Hold on. Complex numbers. Can you remind us what those are in this context and why they're important?
Think of complex numbers as a point or two-dimensional plane each with a magnitude and a phase. The FFT produces complex valued outputs, and the mod RealU, unlike regular activation functions, can handle these complex numbers directly.
Okay, so why is that important? What does the mod RealU actually do with these complex numbers?
Imagine you're listening to that orchestra again. The mod RealU is like a special sound engineer who can selectively dampen the volume of certain instruments without changing their individual tuning or timing.
So it's like a very precise volume control that preserves the essential character of each instrument while ensuring that the overall sound is balanced and clear.
Exactly. And in the case of FT, this selective dampening applied to the magnitudes of the complex numbers introduces a crucial element of nonlinearity.
Okay. I remember you mentioned nonlinearity before. Can you remind us why that's so important in AI models?
Think of it this way. If you only have straight lines, you can't draw a curve. Nonlinearity is like having those curved lines allowing the model to capture more complex, nuanced relationships within the data.
So the mod RealU is like giving FFT the tools to draw those more intricate patterns and understand those subtle connections within the data.
Precisely. It gives the model the flexibility it needs to deal with the complexities of real-world data, which is rarely simple and linear. And by operating directly on those complex numbers in the frequency domain, the mod RealU does this in a way that's both efficient and mathematically elegant.
I'm starting to see why this paper is making waves. We've got speed, accuracy, and now we've got this added layer of expressive power thanks to the mod RealU. And sounds like the authors have really hit on something special here.
And the best part is, this isn't just some random idea they threw together. The paper is backed by solid theoretical justifications for why this approach works so well. They've really thought this through from both a practical and a theoretical perspective.
All right, now I'm really intrigued. Let's dive into that theoretical foundation. Why should we believe that FFT can be this efficient and effective, alternative to self-attention? What's the underlying logic here?
Well, there are a couple of key principles at play here that really under the effectiveness of FFTNet. First, we have the principle of global mixing, which is guaranteed by the very nature of the FT. Remember how we talked about the FFT breaking down the data into its frequency components and how each data point influences all of those frequency components?
Right. It's like each instrument in the orchestra contributes to the overall sound, even if it's only playing certain notes.
Exactly. And because of this inherent property of the FFT, we achieve a global understanding of the relationships within the data without having to do those pair-wise comparisons like in self-attention.
So, we're getting the benefits of global awareness without the computational burden. That's pretty neat. But you mentioned there was another crucial piece to the puzzle, something about energy preservation. What's that all about?
This is where it gets really interesting from a mathematical perspective. It's called Parsel's theorem, and it essentially states that the FFT doesn't lose any important information during the transformation process. The energy of the original signal is preserved in the frequency domain. Think of it like this. When you separate out the instruments in an orchestra, you're not losing any of the individual notes, you're just rearranging them in a way that's easier to analyze.
So, we're not sacrificing any crucial details just to gain efficiency. That's reassuring. But I have to admit, I'm still a little fuzzy on how this whole FFT process actually works in practice. What's happening step by step?
Okay, let's break it down. Imagine you have a sentence and it's represented as a series of word embeddings where each word is converted into a vector of numbers that captures its meaning. The first step is to transform this sequence of word embeddings into the frequency domain using the FFT.
Right? That's our magical orchestra separator. But what's actually happening mathematically during this transformation?
We apply something called the discrete Fourier transform matrix to our input sequence, and this matrix has a special property. It's unitary, meaning its conjugate transpose multiplied by itself gives you the identity matrix.
Okay, I'm going to be honest, that sounds a bit intimidating. Can you break that down for me? What does that unitary property actually mean in a practical sense?
It's simpler than it sounds. Think of it this way. The unitary property ensures that the relationships between the words in the sentence are maintained even though we're now looking at them through this frequency lens. It's like rearranging the furniture in a room. You're changing the layout, but you're not getting rid of any of the pieces.
Okay. So, we're not losing any information about how the words relate to each other. We're just rearranging that information in a way that's more efficient to process.
Exactly. And this is crucial for capturing the global interactions between the words just like self-attention aims to do. But the beauty of it is that we're achieving this global mixing in a much more efficient way thanks to the FFT.
Got it. So, step 1 is transforming the data into the frequency domain using the FFT, making sure we preserve those crucial relationships between words. What happens next?
Now comes the adaptive part where FT really shines. We apply a learnable spectral filter to the frequency domain representation. And this filter acts like a gatekeeper deciding which frequency components are most important for the task at hand. It's like having a sound engineer tweaking the levels for each instrument in the orchestra to create the perfect balance.
So the filter is dynamically adjusting which frequencies get emphasized or suppressed, just like a sound engineer adjusts the volume for each instrument. But how does it know which frequencies to focus on? Is it just random?
That's where it gets really clever. The filter is guided by a global context vector which encapsulates information about the entire input sequence. It's like giving the sound engineer a score that shows them the overall structure of the music, helping them make informed decisions about which instruments to emphasize.
So the filter isn't just randomly tweaking frequencies. It's using this global context to make intelligent decisions about which parts of the data are most relevant.
Precisely, in this learning process where the filter figures out which frequencies to focus on is driven by a multi-layer perceptron or an MLP. You can think of it as a mini neural network within the larger FFT architecture.
The MLP, we've encountered those before. They're like the brainy workhorses of AI, crunching numbers and making decisions.
So this MLP is taking the global context and figuring out how to adjust the filter. You got it. The MLP takes the global context vector as input and outputs a set of parameters that control the spectral filter, a bit like a conductor giving instructions to the musicians.
So the MLP is analyzing the score, figuring out which instruments need to be louder or softer, and then giving those instructions to the filter. That's pretty amazing.
And these instructions come in two flavors, a multiplicative scale and an additive bias. The scale acts like a volume knob amplifying or reducing the contribution of certain frequencies, while the bias is like shifting the frequency bands up or down.
Okay, so we've transformed our data into the frequency domain, And we've applied this intelligent filter that's selectively amplifying or attenuating certain frequencies. What's the next step in this signal processing adventure?
Now we bring in the nonlinear magic of the mod-ru activation function. This is where FFT really starts to flex its muscles in terms of expressive power.
Right. The mod-ru, we talked about how it operates directly on those complex numbers produced by the FFT, which allows it to introduce nonlinearity without messing up the delicate balance of information in the frequency domain. But I'm still a little hazy on how it actually works. What's it doing to those complex numbers?
Imagine a complex number as a point on a two-dimensional plane with a magnitude and a phase. The mod ReLU applies a ReL-like threshold to the magnitude, meaning it sets any magnitudes below a certain threshold to 0. It's like silencing the really quiet instruments in the orchestra, those that aren't contributing much to the overall sound. So, it's like a noise gate getting rid of the extraneous sounds and letting the important ones shine through.
Exactly. But here's the crucial part. It leaves the phase untouched. Remember, the phase encodes important information about the timing and relationships between different frequency components. It's like preserving the rhythm and harmony of the music even as we adjust the volume of the individual instruments.
That's a really clever way to introduce nonlinearity without distorting the essential character of the data. It's like adding depth and richness to the music without changing the underlying melody.
You're getting it. And this nonlinear transformation is essential for capturing those complex higher-order interactions within the data that linear models just can't handle. It's what allows FFTNet to model those subtle nuances and patterns that make real-world data so interesting and challenging.
This is all starting to click for me now. So, we've done the FFT, applied the adaptive filter, and added the nonlinearity with the mod ReLU. What's the final step in this process? Do we just leave the data in the frequency domain?
Not quite. The last step is to bring it all back home to the original domain, using the inverse Fast Fourier Transform or FFT. Think of it as reconstructing the full orchestra from its individual instruments. Now with those carefully adjusted volume levels and added nonlinear richness.
So we're essentially reversing the initial FT, bringing everything back to a format that the rest of the AI model can understand. It's like listening to the full orchestra again, but now it sounds even better than before thanks to all processing we did in the frequency domain.
Exactly. And the output of this IFFT is a sequence of vectors that incorporates all the information captured through the frequency domain processing, ready to be fed into the next layers of the AI model, just like the output of a traditional self-attention layer.
So we've taken this detour through the frequency domain, but we've arrived at the same destination with the added bonus of increased efficiency and expressive power.
Precisely. And this entire process from the initial FFT to the final IFFT is remarkably efficient thanks to the computational advantages of the FFT algorithm. It's like finding a shortcut through the jungle that not only gets you there faster, but also gives you a more scenic route.
I love that analogy, but you mentioned earlier that this approach is grounded in some solid theoretical principles. Can you expand on that? What are the key theoretical justifications for why this works so well?
Well, the theoretical foundation rests on a couple of key pillars. One of them is the concept of global mixing, which stems from the nature of the FFT itself. Remember we discussed how the FFT breaks down the data into its frequency components, and each data point affects all those frequency components.
Yeah, like how each instrument in the orchestra contributes to the overall sound even if it's only playing certain notes.
Exactly. And because of this intrinsic property of the FFT, we gain this global understanding of their relationships within the data without having to perform all those pair-wise comparisons like we do with self-attention. So, we are reaping the rewards of global awareness, but without the computational overhead. That's pretty slick.
Right, and it's not just about global mixing. There's another crucial element in play here that relates to energy preservation.
Oh yeah, you mentioned that before, something about a theorem.
Precisely, it's called Paul's theorem, and it basically states that the FFT, it doesn't lose any essential information during the process of transformation. The energy of the original signal, it remains intact in the frequency domain.
So it's like, okay, when you separate the instruments in an orchestra, you're not actually losing any of those individual notes. You're just sort of rearranging them in a way that's easier to grasp.
Exactly. So we're not sacrificing those crucial details just to gain efficiency.
That's definitely reassuring. I have to admit, though, I'm still a little hazy on how this whole FFT process unfolds in practice, like what's actually happening step by step.
Sure, let's break it down. Imagine we have a sentence and it's represented by a series of word embeddings where is converted in a vector of numbers to capture its meaning. Meaning the initial step is to transform the sequence of word embeddings into the frequency domain using the FFT.
Got it. So that's our trusty orchestra separator.
But what's actually going on mathematically during this transformation?
We apply something called the discrete Fourier transform matrix to our input sequence. Now, this matrix has a special property. It's unitary. This means that when you multiply its conjugate transpose by itself, you get the identity matrix.
Okay, full disclosure, that sounds kind of intimidating. Could you break that down a bit? What does that unitary property actually mean in practical terms?
It's less complex than it sounds. Think of it like this. The unitary property makes sure that the relationships between the words in the sentence, they stay intact even though we're now viewing them through this frequency lens.
Oh, okay. So it's kind of like if you rearrange the furniture in a room, you're changing the layout, but you're not getting rid of any of the pieces.
Exactly. So, we're not losing any of the information about how the words relate to each other. We're just rearranging that information in a more efficient way for processing.
Right, so it's all about smart organization.
Got it.
So step one is transforming the data to the frequency domain using the FFT, being careful to preserve those relationships between the words. Then what happens?
Then comes the adaptive part, and this is where FFT truly shines. We apply a learnable spectral filter to the frequency domain representation. This filter works like a gatekeeper deciding which of the frequency components are the most important for the specific task we are working on.
So it's kind of like having that sound engineer adjusting the different levels for each of those instruments in the orchestra to create that perfect harmony and balance.
Exactly. And during this learning process, the filter figures out which frequencies to focus on. And this is guided by a multi-layer perceptron, or what we call an MLP. You can think of it as this little neural network that lives within the bigger architecture of the FFT.
Right, the MLP, those are like the workhorses of AI, right? Crunching all those numbers, making those decisions. So this MLP is taking the global context and figuring out how to adjust the filter.
You got it. The MLP takes that global context vector as input, and it outputs a set of parameters that control the spectral filter.
So the MLP is like the conductor analyzing the score, figuring out which instruments need to be adjusted, and then relaying those instructions to the filter. That's fascinating.
Exactly. And these instructions come in a couple of forms. There's multiplicative scale, and there's an additive bias. So the scale acts kind of like a volume amplifying, or reducing the contribution of certain frequencies, while the bias shifts the frequency bands either up or down.
Okay, so we've transformed the data into the frequency domain, applied this very smart filter. What's the next exciting step in this signal processing adventure?
Next, we introduced the magic of the mod-real activation function. This is where FFT really flexes its muscles in terms of expressive power.
Okay, the mod-ReLU, we've talked about this, how it works directly on those complex numbers that are produced by the FFT. This allows it to add nonlinearity without messing up that delicate balance of information in the frequency domain. Can you remind me how it actually works on those complex numbers?
Well, picture a complex number as a point on a 2D plane, right, with magnitude and phase. The mod ReLU, it applies a ReLU like threshold to the magnitude. Basically, it sets any magnitude that's below a certain threshold to 0.
Ah, okay. So it's kind of like silencing those really quiet instruments that aren't really contributing too much to the overall sound.
You got it. But here's the key part. It keeps the phase untouched. And remember the phase, it holds important information about the timing and the relationships between the different frequency components.
Right, so it's like we're preserving that rhythm and harmony of the music even as we adjust the volume of each instrument. It's a pretty neat way to introduce nonlinearity without distorting the data.
Exactly. And this nonlinear transformation, it's essential for capturing those really complex interactions within the data. The kind that linear models just can't handle. It's what allows FFT to model those subtle nuances and patterns that make real-world data so interesting and challenging to work with.
I'm with you. So we've done the FFT, applied the adaptive filter, added in the nonlinearity with the mod ReLU. What's the final step? Do we just leave the data in the frequency domain?
Almost. The last step is bringing it all back to the original domain. And we do this using the inverse Fast Fourier Transform, or if imagine, like putting the entire orchestra back together after fine, tuning the volume of each instrument, and adding that nonlinear richness.
So, we're basically undoing that initial FFT, bringing it all back to a format that the AI model can work with.
Exactly. And the output from this IFFT. It's a sequence of vectors, and it contains all the information captured by the processing we did in the frequency domain, and it's ready to be fed into the subsequent layers of the AI model, just like what we would get from the output of a traditional self-attention layer.
Oh wow, so we've taken this round trip through the frequency domain but ended up at our destination, but now we have the added benefit of better efficiency and expressive power. It's pretty amazing how all these pieces fit together.
Exactly. And the entire process from the FFT to the IFT, it's incredibly efficient thanks to the computational advantages that the FFT algorithm brings to the table.
Okay, so we've talked a lot about the technical details of FFTNet, but I think it's important to step back for a moment and consider the bigger picture. What does this paper tell us about the future of AI research?
Well, I think it's a strong testament to how important interdisciplinary thinking really is. By drawing inspiration from the field of signal processing and embracing the elegance of the FFT, the authors have opened up a whole new avenue for creating more efficient AI models.
That's like they've shown us there's a whole other set of tools out there, and sometimes those tools can be incredibly powerful when we apply them to new problems.
Absolutely. This paper also shows how important it is to always be questioning our assumptions and exploring fresh perspectives. Self-attention has been a very popular model, but FFT shows us that there are other potentially better paths out there for us to discover.
And you never know, those new paths might lead to even more exciting destinations. It's a really fascinating development in the field.
It really is. And I think this paper also hints at a future where AI models are more accessible and can be used in a wider variety of applications by reducing that computational burden. FFT opens up possibilities for running complex AI on devices with limited resources.
That's a really cool thought. Imagine being able to bring the power of AI to everything like smartphones and tiny sensors. It could really change how we interact with the world.
Absolutely. The potential applications are just huge. And it's all thanks to research like this pushing the boundaries and paving the way for a smarter future.
It's been an incredible journey exploring the potential of FFTNet. It's safe to say that this paper has left its work on the world of AI. What an exciting time to be following all of this.
It really is. It's a powerful reminder that the world of AI is constantly evolving with surprises waiting around every corner. Who knows what other revolutionary ideas are just waiting to be uncovered? The future of AI is bright.
Well said. This Linkfitty's deep dive has been amazing. To our listeners, stay curious, like and subscribe, and we'll be back soon with another deep dive into the cutting edge of AI. Until then, keep exploring.